For millennia, humanity has gazed upwards, captivated by the twinkling tapestry of the night sky. From ancient civilizations marking seasons by the stars, to modern observatories peering into the universe's deepest reaches, our quest to understand the cosmos is an enduring testament to human curiosity. This journey, beyond the cosmic veil, will explore the awe-inspiring scale of the universe, unraveling its profound mysteries and discovering our place within its immense grandeur. We will delve into realms far beyond our earthly perception, where the familiar laws of physics stretch to their very limits, offering breathtaking insights into the fabric of reality itself. Our story begins not with stars or planets, but with singularity itself. Imagine a time before time, a space before space, all compressed into an infinitely small, dense point. This was the cosmic egg from which everything we know, everything we see, and everything we are suddenly burst forth. The sheer magnitude of this initial event, known as the Big Bang, defies conventional understanding, yet it remains the cornerstone of our current cosmological model, a pivotal moment of creation that set the stage for all existence. In the immediate aftermath of the Big Bang, the universe was an unimaginably hot, dense soup of fundamental particles. Quarks and leptons zipped around at incredible speeds, unable to form stable structures as the energy was simply too great. This primordial plasma glowed with an intense heat, expanding and cooling at an astonishing rate. It was a chaotic, fervent environment, yet within this chaos lay the seeds of all future cosmic structures, patiently waiting for the universe to temper itself enough for complexity to emerge. As the universe expanded, it naturally cooled. After approximately 380,000 years, the temperature dropped sufficiently for electrons to combine with atomic nuclei, primarily hydrogen and helium, forming the first stable atoms. This epoch, known as recombination, was pivotal. The universe suddenly became transparent to light, allowing photons to travel freely for the first time. This ancient light, stretched and cooled by billions of years of expansion, is what we now detect as the cosmic microwave background, a faint echo of the universe's infancy. The early universe was not perfectly uniform. Tiny quantum fluctuations, ripples in the fabric of space-time amplified by cosmic inflation, created slight variations in density. These minuscule overdensities, areas slightly more crowded, would become the gravitational seeds for everything that followed. They were the subtle imperfections necessary for structure to emerge from the smooth, expanding void, the very first blueprints for galaxies, stars, and ultimately, us. Gravity, the invisible architect of the cosmos, began to work its magic on these early density fluctuations. Over hundreds of millions of years, the slightly denser regions, slowly but inexorably, began to pull in more matter. This process was incredibly slow at first, like microscopic ripples gathering dust. But as patches grew, their gravitational pull strengthened, accelerating the accumulation of cosmic material. This gentle, persistent tug formed the building blocks of the cosmic web. Out of this cooling, expanding universe, the first stars began to ignite. These pioneering celestial bodies, known as population 3 stars, were immensely massive and short-lived, composed almost entirely of hydrogen and helium, the only elements forged in the Big Bang. Their birth marked a monumental shift, transforming the dark, neutral universe into one filled with light and heat, ushering in the cosmic dawn. These first stars were cosmic alchemists. Within their scorching cores, through the immense pressures of nuclear fusion, they began to forge heavier elements for the very first time. Hydrogen fused into helium, and then helium into carbon, oxygen, and even iron. This process was fundamental, as these elements, essential for planets and life, simply did not exist before these stellar furnaces roared to life. The lives of these colossal first stars were spectacularly brief, often lasting only a few million years. They met their end in cataclysmic explosions known as hypernovae, events far more powerful than typical supernovae. These explosions dispersed the newly forged heavy elements throughout the nascent universe, enriching the interstellar medium and providing the crucial raw materials for future generations of stars and planets. As more stars formed and died, the universe became progressively richer in elements beyond hydrogen and helium. These later generations of stars, known as population 2 and I stars, formed from gas clouds already infused with heavier elements. This chemical evolution was a slow, continuous process, gradually transforming the pristine early universe into the chemically diverse cosmos we observe today. The gravitational collapse continued, not just forming individual stars, but also larger structures. Dense knots in the cosmic web began to attract vast collections of stars, gas, and dust, leading to the formation of the first galaxies. These proto-galaxies were often irregular and chaotic, frequently colliding and merging in a dance of cosmic accretion, slowly laying the foundation for the diverse galactic landscapes we see today. Our own galaxy, the Milky Way, is a majestic spiral spanning over 100,000 light-years. It's a vast island universe, home to billions of stars, countless nebulae, and our very own solar system. Its iconic spiral arms are regions of active star formation, appearing brighter due to the presence of young, hot, blue stars, tracing out the majestic spin of this colossal structure. Galaxies come in various shapes and sizes. Spiral galaxies, like our Milky Way, are characterized by their rotating disk and prominent arms. Elliptical galaxies are more spheroidal, ranging from nearly spherical to highly elongated, and typically contain older stars. Irregular galaxies lack a distinct regular shape, often resulting from gravitational interactions or collisions. Each form tells a story of its formation and evolution. Galaxies are not isolated islands, they cluster together bound by gravity. Our Milky Way is part of the local group, which includes the Andromeda Galaxy and numerous smaller dwarf galaxies. These groups, in turn, form superclusters, vast, filamentary structures that are the largest known formations in the cosmos, resembling a colossal cosmic web with enormous voids in between. Deep within one of the Milky Way's spiral arms lies our solar system, born from a vast, rotating cloud of gas and dust called a solar nebula. This nebula, enriched with heavier elements from previous stellar generations, began to collapse under its own gravity, gradually spinning faster and flattening into a disk, setting the stage for the birth of our Sun and its accompanying planets. At the heart of this spinning disk, most of the material gathered, compressed under immense gravity, and eventually ignited into our Sun, a relatively average yellow dwarf star. Its birth marked the beginning of a stable, long-lived energy source that would warm and illuminate the nascent planets forming in the surrounding disk. The Sun's radiant energy became the driving force of our solar system. The remaining gas and dust in the disk continued to collide and accrete, forming planetesimals, small, rocky, or icy bodies, ranging from kilometers to hundreds of kilometers in size. These planetesimals then gravitationally attracted one another, gradually growing into the larger protoplanets, in a slow but steady process of cosmic construction. The inner solar system, hotter due to proximity to the Sun, saw the formation of the rocky, terrestrial planets: Mercury, Venus, Earth, and Mars. Here, only materials with high melting points could condense, leading to planets made primarily of silicates and metals, with relatively thin atmospheres shaped by volcanic activity and solar wind. Further out, where temperatures were colder, the giant gas planets formed: Jupiter, Saturn, Uranus, and Neptune. These giants rapidly accumulated vast amounts of hydrogen and helium gas, along with ice, growing to enormous sizes and dominating the outer solar system with their immense gravitational pull and numerous moons. Beyond Neptune lies the Kuiper Belt, a vast ring of icy bodies, including dwarf planets like Pluto. Further still, the Oort cloud, a theoretical spherical shell of icy planetesimals, extends almost a light-year from the Sun. These regions are the cosmic deep freeze, reservoirs of ancient material, remnants from the solar system's formation that occasionally send comets streaking towards the inner planets. Our Earth is uniquely positioned within the Sun's habitable zone, often called the Goldilocks zone, where temperatures allow liquid water to exist on its surface. This precious liquid, along with a protective atmosphere, a magnetic field, and a stable orbit, creates the ideal conditions for complex life to not only emerge, but thrive and evolve over billions of years. However, Earth is not static. Our planet is a dynamic system, constantly shaped by geological forces. Plate tectonics, volcanic activity, and weathering continuously reshape its surface, driving cycles of element circulation and contributing to the long-term stability of the climate, processes that are crucial for sustaining life over geological timescales. The Moon, Earth's constant companion, plays a vital role in stabilizing our planet's axial tilt, which in turn moderates our climate and prevents extreme seasonal variations. Its gravitational pull also drives the ocean tides, influencing biological rhythms and shaping coastal ecosystems, demonstrating its profound impact on life on Earth. The search for life beyond Earth, known as astrobiology, hinges on finding extraterrestrial environments that mirror some of Earth's key features. Scientists look for stable energy sources, the presence of liquid water, and a diverse range of chemical elements. The discovery of such environments, even without direct evidence of life, immensely broadens our understanding of the cosmic potential for biology. The past few decades have witnessed a revolution in planet hunting. Techniques like the transit method, where scientists observe a slight dip in starlight as a planet passes in front of its star, and the radial velocity method, detecting stellar wobbles caused by a planet's gravitational tug, have allowed us to discover thousands of exoplanets. Our understanding of planetary systems beyond our own has exploded. These discoveries reveal a universe teeming with planets. In fact, there appear to be more planets than stars in our galaxy. Some exoplanets defy our solar system's models, like hot Jupiters orbiting incredibly close to their stars, or super-Earths, rocky planets significantly larger than our own. This diversity challenges and expands our theories of planet formation. One of the most compelling frontiers of exoplanet research is the hunt for potentially habitable worlds. Scientists use sophisticated telescopes to analyze the atmospheres of distant exoplanets, searching for biosignatures, gases like oxygen, methane, or ozone that, on Earth, are strongly associated with living organisms. Detecting these could be a major breakthrough. The Kepler Space Telescope, launched by NASA, was a groundbreaking mission dedicated to discovering exoplanets using the transit method. It observed a single patch of sky for years, meticulously counting the subtle dimmings of distant stars. Its data revolutionized our understanding of planetary abundance, proving that planets are incredibly common throughout the galaxy. Following Kepler, missions like TESS, the Transiting Exoplanet Survey Satellite, are taking up the mantle, surveying nearly the entire sky to find exoplanets orbiting bright nearby stars. These closer worlds are ideal targets for follow-up studies, allowing for more detailed atmospheric characterization by newer, more powerful telescopes. The James Webb Space Telescope, with its unparalleled infrared capabilities, represents a monumental leap forward in exoplanet characterization. It can peer through obscuring dust, detect faint heat signatures, and analyze the subtle chemical fingerprints of exoplanet atmospheres with unprecedented precision, bringing us closer to understanding these distant worlds than ever before. The search for extraterrestrial intelligence, or SETI, is a bold endeavor. Instead of looking for life's chemical signatures, SETI projects seek artificial signals, like radio transmissions, that might indicate technological civilizations. While no definitive signals have been detected, the search continues, fueled by the hope of discovering cosmic companions. The Fermi paradox, named after Enrico Fermi, poses a profound question. If the universe is so vast and potentially teeming with life, where is everyone? With billions of galaxies, each with billions of stars, and presumably countless habitable planets, the apparent silence of the cosmos remains one of humanity's greatest unanswered questions, sparking numerous theories. Theories attempting to resolve the Fermi paradox range from the Great Filter hypothesis, suggesting a significant barrier to life's development or longevity, perhaps an inevitable self-destruction, to the rare Earth hypothesis, positing that the specific conditions for complex life on Earth are exceptionally uncommon. Others suggest advanced civilizations might simply be too far away or too uninterested in us. Beyond the familiar stars and galaxies lies one of the most enigmatic phenomena in the universe: the black hole. These cosmic behemoths are regions of space-time where gravity is so strong that nothing, not even light, can escape. They form from the catastrophic collapse of massive stars, crushing matter to unimaginable densities. The boundary around a black hole from which nothing can escape is called the event horizon. Crossing this invisible threshold means a one-way trip, irreversible, as the escape velocity exceeds the speed of light. While we cannot visually observe the singularity itself, the intense gravitational effects around the event horizon provide circumstantial evidence of a black hole's presence. There are primarily two types of black holes. Stellar mass black holes, typically a few to tens of times the mass of our Sun, are born from the collapse of individual massive stars. Supermassive black holes, on the other hand, are millions to billions of times the Sun's mass and reside at the centers of most large galaxies, including our own Milky Way. Our own Milky Way galaxy harbors a supermassive black hole at its core, named Sagittarius A star. Though immense, its presence is mostly inferred by observing the rapid, highly eccentric orbits of stars in its immediate vicinity. These stellar motions provide undeniable evidence for a colossal, unseen gravitational anchor. Quasars, short for quasi-stellar radio sources, are some of the most luminous and energetic objects in the universe. They are powered by supermassive black holes at the centers of young, active galaxies, gobbling up vast amounts of gas and dust. As material spirals into the black hole, it heats up to extreme temperatures, emitting brilliant jets of radiation, making them visible across cosmic distances. The gravitational pull of black holes can warp the fabric of spacetime, a phenomenon predicted by Albert Einstein's theory of general relativity. This warping can act as a giant cosmic lens, bending the light from distant objects around the black hole, creating distorted, multiple or magnified images of background galaxies, a phenomenon known as gravitational lensing. Detecting gravitational waves, ripples in spacetime caused by violent cosmic events, like the collision of black holes or neutron stars, has opened a new window into the universe. Observatories like LIGO and Virgo measure these tiny distortions, providing direct evidence of black hole mergers and insights into the most extreme gravitational environments. The universe is not just filled with visible matter, stars, gas, galaxies. A significant portion of its mass and energy is, surprisingly, invisible to us. Scientists have discovered that approximately 27% of the universe is composed of something called dark matter, a mysterious substance that does not interact with light or other electromagnetic radiation, making it impossible to directly detect. The existence of dark matter is inferred from its gravitational effects. Galaxies rotate faster than visible matter alone can account for, and galaxy clusters are held together by more gravity than their visible stars and gas provide. Dark matter provides the extra, glue, needed to explain these observations, holding structures together on cosmic scales. While dark matter acts as the gravitational scaffolding for the universe, dark energy is something entirely different. It's an even more perplexing component, responsible for the accelerating expansion of the universe. Instead of slowing down due to gravity, the cosmos is speeding up, driven by this mysterious, repulsive force. The discovery of dark energy in the late 1990s was a monumental shock to cosmology. Observations of distant supernovae, acting as standard candles to measure cosmic distances, revealed that the universe's expansion was not decelerating as expected, but rather accelerating. This fundamentally changed our understanding of the universe's ultimate fate. The nature of dark energy remains one of the greatest mysteries in modern physics. Proposed explanations include a cosmological constant intrinsic to spacetime itself, or a dynamic, quintessence, field that changes over time. Unraveling the nature of dark energy is key to understanding the universe's destiny. Supernovae are some of the most powerful explosions in the cosmos, marking the spectacular death throes of massive stars. Type 2 supernovae occur when a star exhausts its nuclear fuel, its core collapses, and then rebounds in a catastrophic explosion. These events are so bright, they can briefly outshine an entire galaxy. Neutron stars are the incredibly dense remnants left behind after a Type 2 supernova. Imagine the mass of our Sun compressed into a sphere no larger than a city. A teaspoon of neutron star material would weigh billions of tons. Their incredible density makes them nature's densest objects outside of black holes. Pulsars are a specific type of rapidly rotating neutron star that emit beams of electromagnetic radiation from their magnetic poles. If these beams sweep across Earth like a cosmic lighthouse, we detect them as precise, periodic pulses, providing scientists with extremely accurate cosmic clocks to study extreme physics. Gamma-ray bursts, or GRBs, are the most powerful explosions in the known universe, releasing more energy in seconds than the Sun will in its entire lifetime. Long GRBs are often associated with the collapse of very massive, rapidly rotating stars into black holes, while short GRBs are thought to result from the merger of two neutron stars. Gravitational lensing is not just for black holes. Clusters of galaxies, too, are massive enough to warp spacetime. They provide insights into the distribution of both visible and dark matter, as their enormous gravitational fields bend and magnify the light from galaxies behind them, allowing us to study even more distant and fainter objects. Cosmic rays are high-energy particles originating from outside Earth's atmosphere, traveling through space at nearly the speed of light. They include protons, atomic nuclei, and even electrons. While their exact origin is still debated, they are thought to be accelerated by powerful astrophysical phenomena like supernovae or active galactic nuclei. The universe's expansion is not uniform across all scales. On local scales, within galaxies and galaxy clusters, gravity dominates, holding structures together. But on larger, cosmological scales, dark energy takes over, driving galaxies and clusters apart at an accelerating rate, leading to the redshift of light from distant objects. The large-scale structure of the universe resembles a gigantic foam-like or web-like network. Galaxies and galaxy clusters form along vast filaments of matter, surrounding enormous empty regions known as cosmic voids, which are truly the largest structures in the universe, almost entirely devoid of galaxies. The concept of the multiverse, though highly speculative, suggests that our universe might be just one of an infinite number of universes existing alongside each other. These parallel universes could have different physical laws, constants, or initial conditions, offering intriguing possibilities about the nature of reality. One proposed mechanism for a multiverse stems from inflationary cosmology, where the rapid expansion of the early universe might not have stopped everywhere simultaneously. This could lead to a continuous creation of new bubble universes, each branching off from an eternally inflating background, constantly generating new realities. The search for fundamental particles continues at facilities like the Large Hadron Collider, or LHC. By smashing particles together at near light speed, scientists recreate conditions present moments after the Big Bang, searching for new particles and forces that could explain dark matter, dark energy, or even extra dimensions. The Standard Model of Particle Physics describes the fundamental forces and elementary particles that make up everything we observe. It successfully explains 3 of the 4 fundamental forces: the strong, weak, and electromagnetic forces, leaving gravity as the elusive outlier. The Higgs boson, a particle discovered at the LHC, is crucial to the Standard Model. It gives mass to other fundamental particles, stemming from their interaction with the omnipresent Higgs field. Its discovery completed a major piece of the particle physics puzzle, confirming long-standing theoretical predictions. One of the biggest challenges in physics is unifying general relativity, which describes gravity on large scales, with quantum mechanics, which governs the universe at its smallest scales. A true theory of everything remains elusive, but theoretical frameworks like string theory and loop quantum gravity offer potential pathways. String theory proposes that the fundamental constituents of the universe are not point-like particles, but tiny, vibrating one-dimensional strings. Different vibration patterns of these strings give rise to different particles and forces, including gravity, offering a potential path towards a unified theory. Loop quantum gravity, another contender for a theory of everything, suggests that space-time itself is quantized, meaning it's made up of discrete, indivisible units, like pixels on a screen, but incredibly small. This theory attempts to reconcile gravity with quantum mechanics by quantizing space-time itself. The origin of life on Earth, abiogenesis, remains a profound scientific mystery. While the precise steps are still being investigated, scientists hypothesize that complex organic molecules formed in the primordial soup of early Earth, eventually self-assembling into self-replicating structures, leading to the first living cells. Panspermia is a hypothesis suggesting that life on Earth might have originated elsewhere in the universe and was transported here, perhaps by meteoroids or comets. While it addresses the origin of life on Earth, it simply shifts the question of life's ultimate origin to a different cosmic location. Asteroids, rocky remnants from the early solar system, frequently impact planetary bodies. Studying them provides crucial clues about the conditions and composition of the primordial solar nebula, as they represent pristine, preserved samples of the raw materials from which planets formed. Comets, icy bodies often with spectacular tails, are also relics from the solar system's formation, originating from the outer, colder regions like the Kuiper Belt and Oort cloud. They carry volatile compounds and organic molecules, potentially delivering water and the building blocks of life to early Earth. The Sun, like all stars, will one day die. In about 5 billion years, it will swell into a red giant, engulfing Mercury and Venus, and possibly Earth. It will then shed its outer layers, forming a beautiful planetary nebula, leaving behind a dense, hot core called a white dwarf. White dwarfs are the inert, super-dense remnants of sun-like stars. They slowly cool and fade over billions of years, eventually becoming theoretical black dwarfs, cold, dark, stellar embers, silently drifting through the emptiness of space, a final, quiet end to many stars. The future of the universe largely depends on the mysterious dark energy. If dark energy remains constant, the universe will continue to accelerate its expansion, leading to a big freeze or heat death, where galaxies move beyond each other's observable horizons and stars eventually burn out, leaving a cold, dark, empty cosmos. Another theoretical fate is the Big Rip. If dark energy were to increase in strength over time, it could eventually become so powerful that it would overcome all fundamental forces, tearing apart galaxies, stars, planets, and even atoms themselves, until the very fabric of space-time is shredded. Conversely, if dark energy somehow diminishes or reverses, gravity could eventually win out, causing the universe's expansion to slow down, halt, and then reverse, leading to a big crunch, a cosmic collapse back into a hot, dense singularity, similar to the Big Bang in reverse. Humanity's drive to explore the cosmos is fueled by both scientific curiosity and an innate sense of wonder. From the first steps on the moon to probes reaching interstellar space, our space missions have expanded our horizons beyond imagination, revealing the intricate beauty and profound mysteries of our cosmic neighborhood. Robotic missions like the Mars rover's Perseverance and Curiosity have meticulously explored the Martian surface, searching for signs of past or present life, characterizing its geology, and preparing the way for eventual human missions, bringing us closer to understanding our planetary neighbor. The Voyager probes, launched in the late 1970s, are now in interstellar space, the furthest human-made objects from Earth. Carrying a golden record with sounds and images of Earth, they serve as cosmic time capsules, a testament to humanity's yearning to communicate and explore beyond our home. Advancements in space telescopes like the Hubble and James Webb have provided us with unparalleled views of the universe, capturing breathtaking images of distant galaxies, nebulae, and exoplanet atmospheres. These observatories are our eyes on the cosmos, allowing us to witness processes occurring billions of light years away. The concept of terraforming, modifying a planet's environment to make it habitable for humans, represents a future where humanity could become a multiplanetary species. While still largely theoretical, it sparks imagination about our long-term survival and expansion beyond Earth. The philosophical implications of cosmic discovery are profound. Understanding our place in a vast, evolving cosmos affects our perspectives on life, meaning, and existence. It challenges anthropocentric views and fosters a deeper appreciation for the interconnectedness of all things. One of the most intriguing concepts in cosmology is the possibility of wormholes, hypothetical tunnels through space-time that could connect two distant points in the universe, or even different universes. Though currently theoretical, they offer a tantalizing glimpse into potential shortcuts across the cosmic expanse. Time dilation, a consequence of Einstein's theory of relativity, means that time passes differently for observers in different gravitational fields, or moving at different speeds. Near massive objects or at relativistic velocities, time can slow down dramatically, a verifiable phenomenon that affects GPS satellites. The cosmic calendar, a concept popularized by Carl Sagan, compresses the entire history of the universe into a single Earth year. On this scale, the Big Bang occurs on January 1st, the formation of our solar system in September, and all of human history occupies only the last few seconds of December 31st. Our deepest understanding of the universe comes from studying its earliest moments. By observing the cosmic microwave background, astronomers are essentially looking billions of years into the past, witnessing the universe in its infancy, providing crucial data to validate and refine our cosmological models. The concept of cosmic distances is truly mind-boggling. A light year, the distance light travels in 1 year, is nearly 9.5 trillion kilometers. The closest star to us, Proxima Centauri, is over 4 light-years away. Our galaxy alone is 100,000 light-years across, and the observable universe spans 93 billion light-years. Dark matter experiments are ongoing, deep underground, shielded from cosmic rays, hoping to directly detect weakly interacting massive particles, or WIMPs, a leading candidate for dark matter. These incredibly sensitive detectors aim to catch rare instances of WIMPs colliding with atomic nuclei. Neutrino astronomy is an emerging field, studying neutrinos, elusive, nearly massless particles that interact very weakly with matter, allowing them to travel vast distances through the densest cosmic objects. Detecting them provides a unique window into high-energy events like supernovae and the cores of stars. The study of exoplanetary atmospheres for chemical disequilibrium is crucial for life detection. On Earth, the combined presence of oxygen and methane in the atmosphere is a strong indicator of biological activity, as these gases would rapidly react and disappear without continuous biological replenishment. The search for technosignatures, beyond simple radio signals, includes looking for Dyson spheres, hypothetical megastructures built by advanced civilizations to harness a star's entire energy output. While none have been conclusively identified, the search represents a bold extension of SETI. Despite immense progress, many fundamental cosmic questions remain unanswered. What is the precise nature of dark energy? Are there other universes? Is life common in the cosmos? Or is Earth truly unique? These profound mysteries continue to drive scientific inquiry and philosophical contemplation. The universe is not only vast but also incredibly old. Its age, estimated to be around 13.8 billion years, is determined by measuring the rate of its expansion and extrapolating backward to the Big Bang. This immense timescale allows for the slow, gradual evolution of stars, galaxies, and life itself. The cosmic distance ladder is a series of interconnected methods used by astronomers to determine distances to celestial objects. From parallax for nearby stars to supernovae for distant galaxies, each step builds upon the previous one, allowing us to map the universe on ever larger scales. Astrophysical jets, powerful beams of plasma accelerated to nearly the speed of light, are associated with extreme cosmic phenomena. They are observed emanating from active galactic nuclei, stellar black holes, and nascent stars, acting as cosmic accelerators and shaping their environments. The search for extraterrestrial biosignatures continues to evolve. Future telescopes aim to not just detect gases but also look for signs of surface activity, like seasonal changes in vegetation or artificial lights on night sides of planets, though these remain very challenging to observe. The universe's fine-tuned constants are a source of ongoing debate. Many fundamental physical constants, such as the strength of fundamental forces or the mass of particles, appear to be precisely tweaked for the existence of stars, galaxies, and life. Even a slight variation could render the universe uninhabitable. The baryonic acoustic oscillations, or BAO, are fossilized sound waves from the early universe that imprinted a characteristic scale on the distribution of matter. By measuring this scale, scientists can precisely determine the expansion history of the universe and constrain models of dark energy. The study of exotic matter, like antimatter, also sheds light on the universe's origins. In the early moments after the Big Bang, equal amounts of matter and antimatter were created, but a slight imbalance skewed towards matter allowed our universe to exist, as almost all antimatter annihilated. Cosmic dawn, occurring hundreds of millions of years after the Big Bang, marked the era when the first stars and galaxies formed, reionizing the neutral hydrogen gas that filled the early universe. This era transformed the universe from dark and opaque to transparent and luminous. The universe is constantly expanding, and new measurements are continually refining our understanding of its precise expansion rate, known as the Hubble constant. Discrepancies between different measurement methods, however, hint at new physics yet to be discovered, possibly related to dark energy or exotic particles. The concept of the observable universe describes the portion of the cosmos from which light has had time to reach us since the Big Bang. Beyond this horizon lies the unobservable universe, which may or may not be infinite, but from which we can never receive information. Space weather, caused by solar flares and coronal mass ejections from our sun, can have significant impacts on Earth, affecting power grids, satellite communications, and even astronaut safety. Understanding and predicting these events is crucial for our technological civilization. The formation of the first heavy elements like oxygen, carbon, and iron inside the first stars was a pivotal moment. The recycling of these elements through subsequent generations of stars, supernovae, and stellar winds formed the chemical basis for planets and ultimately carbon-based life. The study of planetary rings, like Saturn's iconic rings, provides insights into celestial mechanics, the dynamics of orbiting particles, and the history of planetary systems. These magnificent structures are thought to be remnants of shattered moons or planetesimals. Asteroid detection and planetary defense are increasing priorities for humanity. Identifying near-Earth objects, or NEOs, that could potentially impact Earth is critical. Missions are being developed to test technologies for deflecting or disrupting hazardous asteroids, safeguarding our planet. The incredible diversity of exoplanetary systems challenges our previous assumptions. Systems with multiple stars, planets orbiting binary stars, and planets far from their stars suggest a much wider array of planetary evolution paths than our own solar system exemplifies. Cosmic structures are hierarchically organized. Stars form within galaxies, which group into clusters, which in turn form superclusters, all embedded within the vast, filamentary cosmic web. This intricate hierarchy reflects the gravitational evolution of matter over cosmic time. The magnetic fields of planets and stars are crucial. Earth's magnetosphere protects us from the sun's harmful solar wind and cosmic rays. Stellar magnetic fields drive solar flares and star spots, influencing the habitability of exoplanets by regulating stellar activity. Discovery of water ice on the Moon and Mars has fueled excitement about future human exploration, as it represents a vital resource for life support and rocket fuel production, potentially enabling sustainable off-world settlements. The scientific method, fueled by observation, hypothesis, experimentation, and peer review, is our primary tool for uncovering the universe's secrets. It's a continuous process of refinement, constantly pushing the boundaries of our knowledge, ensuring that our understanding of the cosmos is ever-evolving and fact-based. We stand at the precipice of a new era of cosmic discovery. Upcoming missions, like the European Space Agency's JUICE mission to Jupiter's icy moons, and NASA's Europa Clipper, promise to reveal if liquid oceans exist beneath their surfaces, potentially harboring extraterrestrial life. The sheer scale of the universe humbles us, yet also empowers us. Every atom in our bodies was forged in the heart of a star billions of years ago. We are literally stardust, intimately connected to the grand cosmic narrative, a tiny but conscious part of the universe reflecting upon itself. The future of astronomy involves ever larger and more powerful telescopes, both ground-based and space-based, pushing the limits of resolution and light-gathering capability. These instruments will allow us to observe exoplanets directly, detect even fainter biosignatures, and peer back to the very first light in the universe. The integration of artificial intelligence and machine learning is revolutionizing astronomy. AI algorithms can sift through vast datasets from telescopes, identify patterns, and detect subtle signals that human eyes might miss, accelerating the pace of discovery in every field, from exoplanets to cosmology. The concept of cosmic consciousness, while not scientifically proven, explores the idea that consciousness itself is an emergent property of the universe, or that the universe itself possesses a form of awareness. It's a philosophical thought experiment that pushes the boundaries of our understanding of mind and cosmos. Public engagement with space science is vital. Programs that inspire children and adults alike foster a deeper appreciation for STEM fields, encourage critical thinking, and ensure that the next generation remains curious and committed to unraveling the universe's remaining secrets. The study of the multiverse, though speculative, offers tantalizing solutions to perplexing problems, such as the fine-tuning of universal constants. If infinite universes exist, each with different properties, then it becomes statistically probable that at least one, like ours, would have conditions suitable for life. The ongoing search for evidence of cosmic inflation, the hypothesized extremely rapid expansion of the universe immediately after the Big Bang, is a frontier of cosmological research. Detecting specific patterns in the cosmic microwave background could provide definitive proof of this transformative event. Understanding the nature of neutrinos, these ghostly particles, continues to be a focus. Their properties, such as their tiny mass and ability to oscillate between different flavors, could offer clues to new physics beyond the standard model, and even explain the matter-antimatter asymmetry of the universe. Life's resilience in extreme environments on Earth, from deep-sea hydrothermal vents to acidic hot springs, expands our understanding of where extraterrestrial life might exist. This extremophile research encourages us to look for life in environments previously thought impossible. The ultimate fate of black holes over unimaginable timescales is a fascinating theoretical problem. Stephen Hawking proposed that black holes slowly evaporate by emitting Hawking radiation. Over truly vast cosmic timescales, even the most massive black holes might eventually dwindle to nothing. The concept of cosmic loneliness, the idea that humanity might be alone in the universe, is a sober counterpoint to the excitement of discovery. If true, it places an immense responsibility upon us to preserve life and intelligence, making our existence all the more precious. Yet, the journey beyond the cosmic veil is far from over. Each discovery opens new questions. Each answer reveals deeper complexities. The universe remains an endless wellspring of wonder, pushing the limits of our imagination and scientific endeavor. We continue to probe the limits of the observable universe, peering back in time to the very first moments of creation and forecasting the far-flung destinies of stars and galaxies. Our tools become sharper, our theories more refined, but the fundamental awe remains. The biggest mysteries still await. What truly lies beyond the cosmic horizon? Are there parallel universes or dimensions beyond our comprehension? The answers, if they exist, are woven into the very fabric of space-time, patiently waiting for humanity to develop the wisdom and technology to unravel them. Every scientific breakthrough, every new image from a distant galaxy, every analysis of an exoplanet's atmosphere contributes to our collective understanding. It is a slow, methodical unraveling of the universe's grand narrative, a testament to the persistent human drive to comprehend the vastness around us. As we conclude this journey, remember that the cosmic veil is not a barrier to be broken, but a metaphor for the limits of our current knowledge. It is an invitation to continue exploring, to question, and to marvel at the infinite possibilities that lie beyond the cosmic veil.